Hello everyone and welcome to the public space. It seems that we don't have technical issues tonight, so we'll be able to have a live show as far as I can see for now. Let's just hope that my neighbor doesn't turn on her cable TV and we will still have the internet. So today is a debate between Bill Gaede, who came on the show last time, and Bill Gaede, of course, is known for the rope hypothesis in physics, an hypothesis that looks at electromagnetic interaction and many other questions, including gravity, through a rope hypothesis. Last time I did my best as a biologist to try to counter his point, but of course, I'm not an expert. Bill, how are you doing tonight?
I'm doing fine. And I think you did a good job last time.
Wonderful. And joining us to offer a more expert view on all this and to offer a true counter to Bill Gaede, we have Peter, who is a naturalist who works in experimental and phenomenological physics, particularly as it relates to testing theories of quantum and classical electrodynamics. How are you doing, Peter?
I'm doing fine, JF. It's nice to meet you.
All right. So maybe we can introduce with Peter, since you come as the challenger. Do you take issue with the rope hypothesis of Bill? And what is your take generally on it?
So I am enthusiastic of some of the ideas that he's presented. There are quite a few there are some aspects that seem to be valuable in that it seems to be an attempt to physicalize interactions. That seems to me a nice step forward. It's not particularly unique in that sense, but any sort of group that any sort of project that tries to get down to the more nitty gritty of what's going on is quite fun.
So, if you can take us through then the kind of opposition that you will be proposing to Bill tonight.
Sure. I did send your handler, I guess he's your handler, some of the main physical contentions on the quantum level. Now, if you want to look, we can go back to the classical level to have a more solid foundation of some of the potential problems on the classical side, so that we make sure that those things are the simple stuff, so it's called that are more everyday phenomena makes sense.
All right. So what are these contentions?
So my first contention that I would try to at least understand would be related to polarization of fields as it relates to these systems. So let's imagine, for example, Phil, that I want to make sure I understand. You have a coil. I'm sure you've done something like this before. You have two antennas where you put a voltage on one of them, and you rotate, say, the other one. Now, if you have a light bulb attached to one of them, it will light up or not light up. Do you have, I had a little bit difficulty trying to figure out why in your system, if I rotate my antenna, would the light bulb light up versus not light up?
All right, so we'll get to Bill to hear his response to this, but while he does that, Peter, if you can find a way to reorganize your mic, is it possible that we're actually hearing your mic from your laptop instead of the one you have close to your mouth? Because I have the feeling that there's lots of noise coming.
Right.
So maybe we can have, we will move to Bill while Peter figures this out. Bill, on this point that he addresses your theory with, and perhaps generally for our audience, if you could introduce your theory and the point of the rope hypothesis.
Yeah, and I think we have to start at a lower level here, primarily because of the audience we have out there. We're talking about people who are not familiar with sophisticated experiments or things that are beyond their reach. Most people are tangentially related to physics. And where I would start, at least the way I look at things, is that in order for the audience to follow, my reply to such issues as raised by Peter, is that we have to establish some foundations. And this takes us to where we were last week in our discussion with you, JFG. And I'm referring to specifically to what I call the golden principle of physics. And that states that, by the way, that's my golden principle. I'm saying that it's the foundation, the number one principle of physics, a sine qua non, non-negotiable principle. And I'm saying physics requires an object. You can't do physics without an object. And so the first question that I would have as an answer is, do you agree with this, Peter? Do you agree that physics does require an object? Because we were not able to resolve that the other day with JFG.
I think the question that he's trying to ask is, can all of nature be described by natural phenomena, but specifically physical phenomena with objects?
I guess the question is as follows. Can there be any phenomenon occurring in the universe if there were no objects, no matter, nothing whatsoever?
Well, to that I might ask, can objects move? It boils down to, yes, I get your point, but yes, I would say probably you're right.
Probably, okay. I guess that's close enough, or the best.
And I say this because so far as we know in the way we perform the mathematics in a literal way, that is what we do, and we minimally assume that to be the case.
Except that that's not what the results are. In other words, the problem I see with physics today is exactly there at the foundations. For example, you present here a case, a specific case. It could be any case. You could talk about, for example, the slit experiment, polarization. Many experiments that a lot of people out there are only tangentially familiar with. Some are not even familiar with them at all. And I'm saying the big problem that I find right now, and there's a big problem in communication between the mathematical community and the lay public, and you'll see a lot of questions because of this in Quora, for example, where people ask questions, and that's because the answers they're receiving from the mathematical community, in no way they can not relate to those answers. Why? Because they're in the motion of concepts. They say, look, we transferred energy, we moved the mass, we warped time, and people say, these are concepts. What do you mean you moved a mass? What do you mean a force? A particle carries a force. What kind of language is that? We're talking about concepts, and people in the mathematical community are in the business of moving concepts. And the question is, can we do that, or can we only move objects? And if we can only move objects, what is an object, and do we require objects in physics?
So to that, I am going to say to your last statement there, I would say that I already partially answered this, in that one can make an interpretation of the mathematics such that you are moving physical objects. It is not inconsistent with current mathematics. Now, your point on communication, I mostly agree. I think there's a problem where there's lots of strange phenomena that we're not so certain of. And generally speaking, at least people in physics are quite conservative in respect to not pinning themselves down to being wrong and putting mud on their face.
I agree there quite a bit, but that means that they don't have the courage to put their careers or their honor on the line.
Right.
If people make a mistake, well, you made a mistake, but to keep that away and keep it up
Sure.
within you, that's not very honorable. I go completely out on the field and I'm saying, look, we need an object to do physics. And if someone has a problem with that, I'd like to hear the other side of that story. Then I go to the next step and say, what is it? If we need an object, we have to define what the word object is, because otherwise all we're saying is, look, we need an X to do physics, but we're not going to define X. No, obviously you need to define what X is. And so that's the next step.
So to this, I would say you do need an X and an objects. You also need, as you say in some of your papers that you write, that you need qualitative descriptions, but you also need quantitative descriptions as well. We can't neglect both. I would also say to that. And certainly certain tests, certain theories or hypotheses, they're not really theories, they're hypotheses, of course, they need to be tested. And the other thing in terms of how conservative some people come up with, they do not necessarily propose experiments, for example, to say in a reasonable amount of time demonstrate that their pet theory is correct. So this is another issue with some of the glorious things people come up with. However elegant they might be, this is another, I would say, shortcoming of people developing theories.
I don't agree that we need to test theories. I don't think we need experimentation. I say has nothing to do with science. Yeah, just like I'm saying, I know people say I'm crazy. What is science? Science is rational explanations. I need to explain. That's all I need to do. And I explain so that someone understands the mechanism that I'm proposing in the case of physics, right?
Yeah.
And I don't test, I don't verify, I don't prove, because that's an individual matter. If you want to prove something in your basement and say, look, I'm going to run a lab, an experiment, and I'm going to try to test your theory, all you're doing is trying to convince yourself whether the theory is correct or not for your belief. But
I disagree there.
But it doesn't. A mechanism is something you don't prove. A mechanism is something you explain objectively so that someone understands.
No, there I would have to disagree because, first of all, I'm not sure why you would need to point to it being an individual endeavor of testing things. We are social creatures. We should try to work together to try to, get things done and actually resolve problems. I would say we're designed that way to some degree. However you'd like to call design, evolution or whatnot. Now, the other thing I would say about the other point you would say is that I can come up with multiple interpretations. The mind is very inventive in coming up with lots of interpretations to describe what's going on. And in fact, there are multiple interpretations describing similar phenomena, and they can all be consistent with all the current natural phenomena that we see. So if you want your interpretation to be valued, then you should put it to the test in order to show that it's the right interpretation. If you don't think it's the right interpretation or you don't care, that's fine. Then I guess you can be an individualist and go ahead and stay in your basement and then go ahead and not demonstrate that what you are saying is accurate.
Yeah, and again, because belief is a personal matter. That's why it's individual. Because one thing is for the prosecutor to explain to the jury what happened or how his theory, whatever it is he's explaining. Another one is for the juror to believe what he just said. Now, as you say, there could be different theories. You have the defense that usually has a different theory than the prosecutor, right? That's why they're fighting in there. And they have two different theories. Each one tries to convince the jury, and through some kind of experiment, it could be, in the court of science, to say it that way. What are we trying to do? We're trying to convince people to believe like we do. And so you have someone who says, well, space-time is warped. That's gravity. The other guy says, well, no, it's gravitons going back and forth, delivering negative momentum.
I get it.
And so on. You have all these different theories, and all we need to do, the impartial viewer out there, we'll call him the juror, all he's got to do is listen and understand, okay, what is your theory? My theory is this one, A. Okay. What is your theory? My theory is B. Okay. He just understands that. He collects that. He reaches his own conclusion, and that's his personal belief, his personal religion. But we are not in the business. Yeah, it is a personal religious, a personal. Do you believe in God? Well, this guy says, yeah, I believe in God. The other guy says, well, I don't believe in God. So who's right? No. He says, I have proof for the existence of God. The other guy says, I have proof for the non-existence. Everybody has proof, but proof means that he has been convinced of his belief, and he's trying to convince someone else of his belief. That's different than science. Science only explains objectively so that you understand, not so that you believe.
So that was quite, I understand where you're coming from. I think there is a little bit of a disconnect. I don't quite know where it's coming from. It seems that since you're talking about objects, you at least are at the moment convinced that there are, this is a little bit more metaphysical than I want to get, and I hope that we do move on from this. It seems that you are playing you are looking for an objective interpretation of reality.
Yeah.
But you do not want to, you are not so confident as to say that other people ought to also be convinced that there's an objective reality.
Exactly. I'm not here to convince anyone. Listen, okay. I'm not here to convince anyone. I'm not here to persuade anyone. I'm not here to recruit anyone. I'm here to explain a theory and a mechanism so that someone understands it, only understands it. Whether you believe in it or not, whether you believe that's the way Mother Nature runs her shop, that's your personal business. That's something in private that you do at home. But you know, at the conference, all I do is explain so that you understand. Now, it's human nature to try to provide evidence, in support of the theory that one has, and that. I do it as well. I'm a criminal as well for that kind of thing. I try to provide evidence. I'm saying, look here and look there. But the point is that, a theory is only an explanation, an objective explanation for the purposes of understanding. As long as we keep that in science and limit that within science, then we're okay. It's only when we try to convince people through evidence and through alleged interpretations, that we get into trouble. That's when we cross the line into religion.
So to this, I would say that if you have some sort of model that predicts things, I know you don't like the word predict, but if it does predict things, it at least points to something that takes another step forward that other models don't have. I mean, yeah, you can go ahead and just talk about the present and be present and look to the present and to the past. But I would say that at least it's sad that one would not want to look to the future and try to say, oh, yes, I'm going to say, and take that next extra step and say, well, my theory is not only describes everything that we know, but it also describes things that we don't know.
Yeah, let me give you a prediction of something we don't know, that we do know, but we don't know, okay? And I predict that tomorrow at 2 o'clock, there's going to be an eclipse of the sun, okay, for example. Okay, where did I get this? Well, I got this from past observations, etc. And I can do this prediction, I can do the calculation and say, look, tomorrow at 2 o'clock, there's going to be an eclipse of the sun. That's a prediction. That's got nothing to do with science. Science is telling me why does the moon fly out of the solar system? What causes the moon to stick to us? Why doesn't, what prevents it from flying out? That would be I can give you another prediction. I let go of the pen and it falls to the floor. And I can predict that consistently, believe me. I'll let go of the pen, it always falls to the floor. And I can say, look, I predict that the next time I let go of the pen, it's going to fall to the floor. That's a prediction. That's got nothing to do with science. Science is telling me why, the cause. What causes the pen to fall to the floor, not to the ceiling. That's science. That's objective. If I can explain that, the mechanism, right, Mother Nature uses to produce that effect, then I'm a scientist.
Okay,
I don't have much
Peter,
more to
go
say.
ahead.
Go ahead, I'm sorry.
Well,
I don't have much more to say to that.
I was
guess
about
the
to
only
say,
thing-
I will just present my own opposition to Bill, and then you can do yours. Bill,
Yes.
when you understand some mechanism or some hypothesis, these things will invoke entities. They will invoke gravity being something or being something else. This will lead to differences. Can you at least acknowledge that there are differences in what is expected when I invoke an explanation versus another? For example, the theory of relativity there is a difference in the mechanism involved in its explanation of gravity with respect to quantum physics, for instance.
For example.
All
Or
right.
even with respect to Newton.
So that
Newton
difference is often what ends up being the prediction. It's often because we say that there is a difference between the two theories, we expect to find different things in the universe when we look for these things.
Yeah, but all you said is we have Newton. Newton said, well, let's assume God does it with particles. Okay, so the sun throws some kind of particle at the earth, and it produces his mass times mass divided by distance squared. That's his theory. Then you have Einstein coming in there and said, look, gravity is the geometry of space-time. Warped space-time produces gravity. So you have these two explanations. Right now, you don't have to believe either one. You can accept one, you can accept the other, or you can accept none. These are explanations. These are physical interpretations for equations. And they said, look, my equation tells me this or leads me to believe this. The other guy says, I have this other theory. But all you need to do as a scientist is be objective and say, okay, I heard you, and I'm going to take them into consideration. What decision you reach, whether you like this theory instead of the other, that's your personal business. That's a belief. That's got nothing to do with science.
I mean, it does have something to do with science to the extent that we can state today that Newtonian mechanics is less precise than relativistic mechanics for a certain domain of physical observation, right? And that's how science theories end up being true or not.
Less precise has nothing to do with science. What does it matter if one is more precise than the other mathematically? What does that tell us about the mechanism?
Well, it tells us that certainly
Einstein's explanation for his more precise theory, does his explanation make any sense? The fact that he's saying that gravity is warped space, the fact that his mathematics is closer to the correct value than Newton's and can predict the value of the Mercury's, perihelion or whatever, more precisely. What does that tell us about the mechanism? The mechanism is that Einstein proposes is that there's a concept, unimaginable concept called four-dimensional space-time, and it's warped, and that causes gravity. That's nonsense. So whatever his precision, whatever advantage his precision gives him has nothing to do with his irrational explanation.
All right. That is true that relativity is not an explanatory theory. However, I know that when we find an explanation, it's going to have to fit with relativity. It's not going to have to fit with Newtonian mechanics.
Who says it doesn't fit with Newtonian? If that were true, JFG, if that were true, NASA would not run their ships with Newtonian mathematics. They do not use relativity at all.
Well, let's hold on for a second. For the most part, Newtonian mechanics is good enough, and it's simpler. In certain domains. It more simply describes nature. There's simpler mathematical objects to deal with. That's why NASA uses Newtonian mechanics. Now, there are physical phenomena qualitatively that you cannot explain, with classical Newtonian optics. Or, for that matter, I don't even see how you can, I don't think it's very easy to even explain with Huygens optics. Wave optics.
Yeah.
So when the eclipse, you brought up the eclipse and you brought up gravity. So I'll bring this experiment up. Of course, the point was that when you look at the night sky, you look at the stars, the big general relativity thing that phenomena that we could not explain, for example, is why when the sun comes, the moon comes in front of the sun, and then we can sort of see we can better be able to see the stars behind the sun. Why do the stars suddenly seem to move closer to the sun? Another phenomena, associated with special relativity, is I have these clocks that click up and down that are very precise, and we know exactly what's going on. And as they orbit around the Earth, the signal that they send to us depends on how fast they're rotating around the Earth. So those two phenomena cannot be explained, I would say, with classical Huygens or particle physics, without special relativity and general relativity to start with.
Yeah, but how does special and general relativity explain them? What is the physical mechanism? What causes the clock to go slower? That's what we want to know.
Sure. And so then the question becomes, with those phenomena, then you need to construct, if you want it to be an objective system, you need to construct an objective interpretation around the principles that you have, that you see. Now, I should point something out, by the way. The Einstein, for example, we did not know that the stars, when the sun comes, when you have eclipse, we did not know that the stars were going to come closer to the Earth. So this is something that he predicted, and it added veracity to his experiment that starts to cast doubt on the other experiments. That's the real power of predicting future events that we don't know might occur.
Yeah, but the fact that you put an equation has not given us an explanation. I'm saying physics, science in general, has to do with explanations, with physical interpretations. The math is irrelevant, totally irrelevant.
No, I
need an
agree.
explanation of how Mother Nature runs her universe. I need to know what gravity is, what physical object is mediating gravity. I need to understand what physical object is mediating magnetism. I need to have the eyes of God to see that invisible mediator in order to have an explanation. That's what we don't have today. We have a lot of math and no explanation.
So to that, I would say I would go back first to perhaps the conservative nature of some physicists, maybe perhaps bolder ones, and it is in the language in which they describe these phenomena. They talk about, for example, the fabric of space-time that bends space. So this you can take to be a physical object. So,
but it's not. That's the point. That doesn't have no relationship whatsoever to physics. That's
why do you say that?
Because it's a concept. Is time a concept or an object?
Is a fabric an object or a concept?
Well, we're talking about the fabric of what? What is this fabric?
Fabric.
The fabric is space-time, and time is a concept. Sure. So we're making a fabric out of concepts here.
How about a fabric in space-time?
Are we saying that space is a physical object? Is that what we're saying here?
Sorry, say it again?
Space a physical object? Is time a physical object? They're not. These are euphemisms. These are figures of speech that have been introduced, like the word particle, which is not a particle. It's not a corpuscle. We're dealing with abstractions. These people are not physicists. They're abstracists, as I call them, because all they do is abstraction. Okay. I need to know a physical object. That's why I'm saying the first principle of physics, we need to have a physical object at the end of the yellow brick road.
All right, so let's take it to the next step, the next level of coming up with, and I can describe some better descriptions of space-time at least we call it space-time as a fabric. Now we will bring this up. And by the way, I can mention, sure. And by the
thing, you know, that space-time is a fabric. Obviously, it's not.
Well, okay, it depends on what you mean by space and time. We would need to define that, sure, but at least we can say that we could have a fabric that has something associated with space, and it seems to change with time. We can at least agree to that.
But that's why I start at the beginning. The beginning is physics requires an object, and we need to define what an object is for the purposes of physics if physics requires an object. Space-time does not qualify as an object, first because it's unimaginable, it's four-dimensional. They say, don't try to imagine this. And then the other one is that you can't draw it, you can't make a picture of it, so what are we talking about?
Who told you don't imagine it? That's a bad feature. That's a bad feature.
Stephen Hawking told me.
Can I read it to you? Can I read it from the guru of physics, so-called physics? I'll read it to you if you don't mind. Just 2 seconds. I think it won't take.
I'm not debating him. I'm debating you.
Look, let me say here. It says, listen to what he says. A four-dimensional space called space-time. It is impossible to imagine a four-dimensional space. Stephen Hawking, in his book, A Brief History of Time. It is impossible to imagine a four-dimensional space. No, because he's trying to imagine a concept. Of course, he can't picture it.
So you're bringing up Stephen Hawking, who was a chair of mathematical physics, as your argument. You're really pigeonholing this statement you're making. Really, so you're picking out. Let's pause for a second.
He's not the only person who has said that. There are lots of physicists say you can't imagine space. In fact, all you have to do is draw it. Just draw it and we'll know. If you can't draw it, obviously there's no such thing as space-time.
I watched a movie recently and they had a four-dimensional space illustrated as a tesseract. It was like cubes, and it was a list of infinite cubes, and you could travel between the cubes, and you find yourself at different point in time. Isn't it a satisfactory illustration, Bill?
No, you have a three-dimensional cube representing a two-dimensional screen. That's what I see. I don't see a four-dimensional anything because no one can even imagine a 4D anything. There's no such thing. The universe entirety from here onto to God, to heaven, all there is 3D. There's no 2D, there's no 1D, there's no 3D, and no 0D, no 4D, no 0D. There's only 3D. And anything outside of 3D does not belong to physics.
So to that, I would disagree. And the way I'm going to...
But that's why we have to say, what is an object?
Let's nail it down. So...
What is an object?
So an object, your point was it has something that has size. By the way, we have to throw away particles because some particles we don't know at least what their size is. Or maybe you would say that they do have size, but we just don't know. I'm not sure where you stand there, by the way. It has shape.
Particles, they say, I've just listened to Mr. Sean Carroll. I assume you heard of him. Sean Carroll says that there are no such things as particles. Stop thinking of particles. He says all particles are fields, vibration of the fields. So we have a field, which is a concept. He says just a bunch of values, and he's saying there's a vibration of all these concepts. So we have no particles even. You know, what are we talking about then? What is this nonsense?
So Bill, did you? Okay, two things. First, I want to make sure that there's not a little bit of disconnect. Did you get the papers that I sent you, or no?
Sure, I did receive it, Peter. Yes, I did.
Okay, thank you, Bill. To this, okay. So I am not Sean Carroll. We're not talking about Sean Carroll. You can go to California and speak to him, I suppose.
For example, let me just for just 1 second. In the four or five here that papers that you sent to me, right, that I looked at, they invoke particles. So hopefully you'll tell me what a particle is in your religion if it's not what Mr. Carroll says.
Sure. There are particles in that paper.
More puzzle.
Yes. Yes. I mean, to mind you, I wasn't the author of any of those papers. Those are historical papers.
I understand. But, if you're
call them particles, they're linguistically shorthand. But of course, my point was only the fact that we don't know what the particle size was. So to say that it has shape, well, that's a little bit uncertain. We are doing experiments, for example, at the moment to come up with precision tests of what is the shape of the electron. We don't know yet. We don't know the electron size because as far as down as we can try to probe it, it seems to have either, it seems to, depending on how we probe it, we run into some problems in that other particles are produced as a result, such as
this is an issue where the theorist has to make an assumption. This is not a question of using a microscope. This is not a question of running an experiment. This is an issue where the person has to step back, do some armchair physics. He steps back and tries to think and says, what could it be? What could it look like? For example, let me give you an example.
And then we'll never know, by the way, because I can come up with, we'll never know really what it is, because the other armchair guy next door will also be able to come up with an equally valid idea. So that's fine.
In science, we have no use for knowledge. So we never know is not important in science. In science, we have to explain. For this, you make an assumption and say, let us assume the electron is a particle, a little ball. Fine. Then we make an assumption. We say, okay, now let me explain the mechanism of, for example, quantum jump, of how an atom works. Then you can explain it. But if then you say, I don't know what an electron looks like, well, who cares what it looks like at that point? At that point, all we need to know is I'm going to make an assumption that it's a ball.
Okay, so then I guess we can say that we maybe don't. So this is interesting in light of your rope hypothesis. Then, asking questions about how does rope behave in certain situations. If I don't know it's the properties of this rope, it becomes challenging for me to actually even identify, does it even conform with known physics, such as the one that I brought up previously, where if you have a light, it's a problem of induction, essentially. It's sort of a unification of the Maxwell's equations. If you have two antennas and you rotate one versus the other, you light up one, it lights up in one configuration and it doesn't light up in another configuration.
Yeah, polarization.
Polarized. Yes.
Yeah. For example, look at that picture you drew there, the one that you've got on the board. I assume that's the star, the blue dot at the top is a star, faraway star, right? And it's that's the sun, or what?
Sure. I mean, it's a picture that you can describe multiple. It was a little bit vague, but we can start with this as being the star. And either objects behind it. Of course, it doesn't need to be directly behind it. It can be slightly behind, but you would otherwise perhaps, or it could even be over here, for example, and then you get some bending due to the star's presence or not. But yes.
Okay. The question is, do we bend or do we deflect? Is it the same thing to say bend to say deflect? I mean, is light a photon? Or are we talking about a beam?
I thought we already established that it's that systems are most likely physical. We don't need to get into semantic arguments. I mean,
it goes to the basic theory. If these are photons, individual photons, then light has not bent. The photon has been diverted, deflected. That's the correct language.
My point is that you are requiring a precision of language.
Yeah, absolutely, because otherwise I don't understand your theory. What are you saying? Are you saying that it's a stick and I bent it? Is that what you're saying? Or are you saying that a little particle just went around the warpage of space-time? Those are different mechanisms.
So then the question becomes, okay, I have my eraser towel, of course. And then the question is, if you put a massive object, say my timer, which I haven't set yet, and for example, I send some sort of particle through it, would you say that bends? I'm not really sure what you're going to describe. So this is quite literally how we describe it. So the object bends other things around it. And then as a result, other particles, which can bend space in the same way, just like a trampoline, the object will move in a different way because of the fabric of the space. Simultaneously, it bends. Now, to your point about, can you imagine something four-dimensional? One could imagine, okay, now how do you just project that to 3 dimensions? And that's tricky.
It's more than tricky, it's impossible.
Now, I don't know why it's impossible. You can describe it.
Because you cannot imagine 4 dimensions to begin with. There is
okay, 4 dimensions. Oh, so one can use analogies, sure. Now, to take your analogy that you used in the past with magnets, for example, if you're in a fluid, for example, and you drop in a magnet, say the fluid is a colloidal fluid, I think it's called. It has little tiny magnets that are all inside of the objects. Little objects will start to bend toward the magnet in the fluid. So this would, if you think of the little colloidal objects as part of the fabric, then you can then talk about other magnets which start moving around inside this little magnetic fluid. To take an example, I know you might like that because it pushes your all electromagnetic theory. I would say, perhaps, by the way, that not all systems interact. Not all particles that we know, at the very least, interact. We don't know, and we would say that we have a strong suggestion to think that they don't all interact by charge. That's one of the biggest problems with the theory. But we'll put that to the side for now, the fact that some particles do not interact because they may not have charge. Neutrinos is the good example, or is the example that we know of that I would say would be the most solid, at least. But I think you get the point.
The analogy you just gave involved only 3D objects. So it's an analogy for something that we are familiar with, but space-time. No one can do an analogy for space-time because there is no 4-dimensional object that we can imagine.
So
is tricky.
It is tricky, yes. But at the very least, it describes the process that's occurring. If, for example, we lived in some sort of fluid, I'm not saying that we do. This would be this would be an ether theory, essentially. We have some sort of fluid such that objects move in that fluid in a way that it bends, I guess, or I don't remember or deflects. It doesn't matter to me, but it moves as a result of this fluid because of other objects. I'm fine with this interpretation. It's perhaps not the only interpretation, but it's an interpretation that could be valid.
But you see, you just said it doesn't matter to you whether it bends or deflects, and it changes your theory. It changes your mechanism. Whether you use a little ball that
hold on. I laid out the model. It's real. I get your need to be precision in words, but very often my only contention in that is that, we use lots of words, and then shorthand in your mind, you might come up with this word or this word and this word, and by mistake, it's hard to conform to this object-oriented worldview. So that's my only. It's really a limitation of my mind to come up with the correct word at the moment. So my only contention with that is, let's not get into that aspect of the semantics, because I understand your point, and I'm not. Let's put the interpretation. I'm granting the interpretation of objective only. That's not the problem here.
But you see that there's a difference, right, between bending a rod. Like if I were to explain to you something, and I said,
I get it.
Bending a rod is not the same thing as swerving a ball, throwing a curveball, for example. These are two different mechanisms. So if we're going to talk about photons, it's not a question of semantics. It's a question that goes to the root of the theory.
Got it.
So, bending of light is a very tricky term, because people keep saying bending of light, and people get the idea that, somehow we're space bent light, when that's not the case. That's not what the guy is saying. The guy is really saying that the bowling ball went around a curve. That's different.
So let's agree to agree, I suppose, on your contention, and let's move on and ask for example, if we take the fluid example of these objects, the question that for the rope hypothesis is, does your model map to a potential? We call this fabric a potential in mathematics. Does this object conform to a potential interpretation of quantum, or I guess classical mechanics?
Well, going again with that picture you've got behind you, I can explain that in a different way than using unimaginable four-dimensional space-time. Listen, just for a second. I can see, look at those lines that you've got behind you. Those lines are the ropes that interconnect the light coming out of that star in the background all the way to the sun, to the corona of the sun, and then relay that signal to the earth. I mean, it's straightforward.
Perfect. Okay, so now I'm going to reorganize this picture. Okay, and we can exchange this. So we've agreed that this is a photon, and we agree that this is a star. But let's change the star to.
I was thinking of the sun.
Okay.
I was thinking of the sun instead of a star, but well, I don't know what you're.
It's the same. Okay. It's the same for this purpose. If you're going to talk about microscopic phenomena, let's move it down to details that we don't know much about gravity, so it's still quite speculative at least. And I know that you wanted to describe those things, but at least you won't have too much disagreement with your rope hypothesis using stars. Okay. Let's get down to the double slit.
Okay.
So you have, for example, your rope. So you have your magnetic rope and your electric rope. Is this accurate? Is it that you have two ropes and that's exactly what's going to get unwind and they come back together? Or are they two separate ropes in the double slit experiment?
We're talking about two separate ropes.
Two separate ropes. All right. So now let me change it a little bit. And I'm going to put, so typically when we do this experiment, okay, one can choose how these, from the source, how they combine, okay?
Okay.
Instead of them coming back and recombining, let's send, say, two, or let's lower the intensity of our light source such that it comes here or here, and we organize our experiment such that it lands either here or here. Why does this occur? Meaning, I'll be more specific. You have apertures, for example. I can move my apertures such that only the light can go through these two directions, or I can change my experiment such that it comes here. The rope is here. The rope would be over here. It would, if I send one light particle at a time, why does the light particle, I only see clicks on my detector here sometimes, and then here other times. This is called a beam splitter, by the way, a beam splitter sound. Do you understand my question?
I think I do. Let's see if I can. You're saying the source is the one on the top, right?
Yep.
Okay. You're saying there's light going to the slits, and then what's that point there, right under the little n?
The point where?
Right above there. That one, yeah. That point there.
This is my light source. This is my light source.
That's the light source. Now, over there you have one. No, right above it, you got a point where it deflects.
This right here?
No, the point that you.
I don't have any other points. What's missing
from
here?
the source goes straight, and suddenly it deflects. You see, yeah, there.
There's no other.
The last one you erased.
That's nothing. It's just a light source we're talking about.
Okay,
but light source.
You're saying that the light goes and somehow deflects?
I'm saying that I'm going to set up my apertures, meaning pinholes.
Yeah.
The pinhole goes through here or goes through here. I have sets of 4 pinholes essentially.
Okay, so you're saying that the rope from the light source is connected to the slit, and the slit is connected to that end, to the screen or the detector.
No, I didn't say that.
Well,
what I said is,
that's what I see.
So classically, okay?
Yeah.
If you shine light here, okay, you'll see light particle, you'll see light, I'll detect a signal here, and I'll detect a signal here. Does that make sense?
Yeah. And what's the problem? With the rope model, you have the light source connected to the slit, to the
intensity of my source.
And the aperture is made out of atoms, and it's relaying the signal to the detector.
So there's an interaction. Okay, that's fine, but we're going to get there. That may be the case. We don't an extra claim, by the way. You've already pinned yourself to an extra interpretation that mathematicians don't necessarily claim occurs. And that's good. But your claim is that somehow there is some interaction with, I don't know, this is empty space, but you're saying that it interacts with the slits?
Well, keep in mind that we don't need the slits to do the slit experiment. That's the first error.
Well, it's useful for us, like sort of forcing the light to go in the direction that we want it to go.
Well, why can't you put a needle? We do it with a needle and it works fine.
But my point is, if you use double slit, then I can force the light particle to go either here or there.
Yeah, but what you're doing by putting the slit, keep in mind.
A slit plus two apertures. Two apertures.
Yeah, by putting the slit, you have the idea, or the mathematicians have the idea, that what's happening here is that light is a photon, so that's already an error. Let's
ignore the interpretation for the moment.
Yeah, but what I'm saying is, see, what you've got there is that you have a rope connected to the slit, and another atom from the slit is connected to with a rope to the detector. That's what you have. So I'm not sure what this changes in any way. You see what I'm saying? I'm saying that
I don't see what you're saying.
You're having a light source, right? The light source is made out of atoms. That's the source of light. And I'm saying that atom there, the one that's being stimulated, is already connected to an atom in the slit. And another atom, or the same atom in the slit, or several of those atoms, are connected with ropes to the detector. So that line, that arrow that you drew, are we're going to replace them with ropes, and we have two sets of ropes connected.
Okay. So if I lower the intensity of the light, I can get a click on my detector either here or here. If I lower the intensity to one particle at a time, or one whatever rope at a time. Sorry, I'll use the word rope. One rope at a time. The rope will see a detector hitting this rope or this rope. One would need to, at the first step, explain why the ropes hit one or the other. By the way, I should mention that this is a phenomenon that occurs not just with ropes. I can do it with electrons as well.
Yeah.
So, Bill,
so what's the question?
He seems to be saying that there is a quantum nature to the reaction we see there. A digital yes or no, the photon passes or doesn't passes, and it can only pass in one of the slits at a time. How does the rope hypothesis approach this question of quantum behaviors of light?
Well, that's why I'm saying what we have here is a problem. And the problem is that we see light as a series of particles. And you cannot explain the slit experiment with particles very simply because we replace the slit with a needle. That's why I'm saying he made it more complicated. We put a needle instead of two slits. And there's no way the particles are going to turn the corner and go inwards. At least you would have to explain by what physical mechanism the particles bend the corner around the needle. Because I've done it with a needle and you produce the fringes anyways. So
there's no bending here, by the way. It's going in a straight line. I designed it such that they're going in straight lines, by the way. No, we don't need to worry about bending of the rope.
Yeah, but I mean, you're not producing the slit experiment. This is not a slit experiment.
This is a slit experiment. There's one slit and another slit. Now the question becomes, what determines whether I can detect the rope on this one or this? Why is it sometimes that atoms on this side interact, and then in other instances the rope interacts with this group of atoms neighboring the slit? You're claiming that somehow, it seems what you're claiming is that there's interactions occurring. One would think, for example, if I make the distances very triangular, one would assume that the interaction between this rope, these particles, and the source, and these particles and the source, it would be about equal. Why does it sometimes interact with these ones more than these ones in your rope hypothesis?
Well, I'd have to look at the experiment to see, how much motion there is. I mean, we'd have to measure and find out if the distances are the same. I mean, I don't know. I'd have to look at this in more detail. But I'm not sure what this explains, because how can you explain this with particles, for example? Same setup. What's the explanation with particles? Because the particle should go also, unless that particle can be at two places at once, which is what quantum says, which is nonsense.
But I would say that we can do this with electrons. Are electrons ropes or electrons?
If electrons are particles, but if electrons are not particles, then it's nonsense also. Because the first thing you would have to explain with electrons. The first thing you would have to explain with electrons is what the atom looks like. If the electron is a bead that goes around the atom, what keeps it tied to the atom? That's the first thing we have to start at the beginning, not at the end. We have to start with the basics. What does an atom look like? Okay,
let's start with an atom, of course. You have protons and neutrons in your nucleus and your electrons. Okay, simple enough. We can do the experiment with atoms at this point. We've advanced in the science such that we can do the same experiment with atoms. Yeah. Now the question becomes, we can see the atoms, which do have a size. The nucleus has a finite size. So I can start talking about shapes of we're going to call that, I think it would make sense to call that a particle. I mean, if you have an interpretation that says otherwise, that it's really made of ropes, then, I mean, I would say this is a distinguishment without too much of a difference.
I have yet to see a picture of an atom. I have yet to see a picture of the quantum atom. What does an atom look like? Can you draw it there? I'm sure you can't, because no one has ever done it. I mean, what does a quantum atom look like? What does it look like? Is it a little bead that's going around the nucleus?
So the problem is that we can probe an electron. We know it is moving. It is moving with respect to the.
That's your interpretation.
It's moving with respect to it. We do know that.
Your interpretation.
No. It's moving with respect to it, and that's not. That is not an interpretation.
You have to draw the atom before you can say that. You have to draw the atom before you can say that.
Okay, fine. Okay, all right. So
just before we get there, I just wanted to show my own image that I found from Google. I don't know if it will convince Bill, but I just wanted to troll a little bit with it. Here's the strontium atom, Bill. What's happening? I got your atom.
What is that?
It's a strontium atom. It's a purple spot right there, right in the middle, a single atom.
Could you make it bigger so that we can really see it?
Okay, let me try to zoom it. Here's your atom.
But hold on. I should say, by the way, that you don't want to look at it because you just want to sit in an armchair and just hypothesize about it. You don't want the experimental to test.
I want to visualize an atom. I want to see what your atom looks like in your head. I want to see what you're thinking about.
Experimentalists
for you to draw that.
You're going to try to pin me down, and that's fine. So you have, for example, we have an idea that there are presumably things inside of a nucleus. We don't quite understand what's inside the nucleus a whole lot. We know we have quarks.
Okay,
and
forget
we
about
have
that.
other.
I want to
We
see
call
the
what we
electron.
call
Where are you
gluons.
going to put the electron? Put the electron somewhere.
Okay, you're gonna
Forget about the nucleus. The nucleus is easy. Let's look at the electron.
So let's assume, for example, let's start with the interpretation, the realist interpretation, because I know you like the realist interpretation. Let's assume you're going to pin me down. That's fine. We don't know this for sure, but we'll pin down that there is an electron that exists in a single point in space. I can detect, so far as I know, I can detect a particle in location. So we can say with a pretty high degree of accuracy that there is something associated with it that is particle-like. This is the electron, and this is my neutron. So I think you understand these parts.
What keeps the electron tied to the nucleus? Why doesn't it fly away? What physical entity keeps the electron tied to the nucleus?
But the mathematics points to photons, and those photons are considered virtual because, hold on, I would say we're called them virtual.
Magical.
That's just it. That's just it might be a misnomer in your. But let's put this to the side.
Not virtual, it's magical.
If you want to look it up on Google, you'd have to look up virtual. Okay.
Yeah, I looked it up.
If you want to take, if you want to take, if you want to take an interpretation, you can talk about an electromagnetic potential, like a potential, just like this potential of space-time. Here, we can talk about a potential associated with we can talk about a fabric which bends the electron moving towards and away from the electron.
What physical entity? I want to know. Potential is not a physical entity.
The fabric, we call it fabric.
What is a fabric? What fabric are we talking about? What fabric?
We don't.
Space?
Electromagnetic fabric.
That's not a physical entity. That's why I'm saying you have to draw an object is that which has shape. You have to draw it.
You're getting too pedantic here. How is a fabric more or less of an entity than a rope?
Well, draw it. What fabric? Show me. You have to draw it. Draw a fabric.
I'm not a great artist, but
no, you don't
I
have
think you
to
get
be
the
one.
point.
What is that? What have you drawn? Are you drawing space? You're saying space is a fabric? That's all between.
I mean, you can draw a rag, Bill. A rag is drawable, and it's a fabric.
I can draw like that one there. I can draw,
okay,
but that's not what's between an electron.
What if Peter? What if I take everything that Peter has said for the last minute and I change the word fabric for rug?
What is between the nucleus and the electron? Bent space-time?
Bent fabric.
What is that? What is that?
What is the rope? What is the rope?
It's a rug, Bill.
About the rope.
I can go to the. What is this bent fabric? What is it?
I don't know. What is? Who knows? What is this bent rope? What is this twisted rope?
I can go to the hardware store and get you a rope. But when you say fabric, what fabric are you?
What is the rope made of? We can ask that question to start with. Do you know what the rope what the real rope is? We don't have.
What is that? What is your fabric made of?
You can say that. Yes, you can ask the same question, but we can't answer this unless you pushing an interpretation. Of course.
You're just trying to elude the question.
There's no cheating there.
This fabric. I've never heard of this fabric in quantum mechanics. I never heard the word fabric in quantum mechanics.
Okay, so we can talk about the fabric because I sent you a paper about it.
Yeah, but then if you're going to talk about the fabric, you better be able to draw the fabric before you can just talk about it. I can draw a rope. You can't draw a fabric. I don't know what that is. That I see a bunch of lines. That's all I see.
If you'd like me to tape the rope, the piece of fabric on the wall, we could do that if you'd like.
Okay, so you're saying
that
the fabric looks like that rug. You're saying that the fabric
is sitting.
You're saying that the fabric looks like that rag.
The fabric, you have I would say a better interpretation is a fluid because it's three-dimensional. It's a fluid. I'm not saying that this is the case, but it's a fluid where you have particles inside this fluid. That would be an ether theory.
Peter, I think that you're improvising with ether.
This is not improvised. I sent you the paper of the potential. The first paper I sent you.
Potential is not a physical object.
They call it potential, but it's a fact. But we call the potential, for all six purposes, the potential is the mathematical object which describes in your interpretation, in your physicalist interpretation. Let's get the mathematical points aside. That doesn't matter in this debate. You're relying. No, you keep on bringing it up. You don't need to bring it up. We're on the same page. But exchange the words potential and fabric only for the purpose of that's the word that I'm more used to saying. That's all.
Okay, let's stay with the fabric. What happens when the electron leaves? Does the fabric stay there? How far does this fabric extend? All the way to the other atom? I mean, what is this fabric? I never heard of this. This fabric
is the. Have you ever heard of a voltage?
Yeah, I heard of field also. Is that what you're referring to? Another word for field?
No, a field is not the same as a voltage.
No. I mean, field is the same thing as a fabric? Is that what you're referring to? Calling it a fabric, a field?
A voltage would be one description of what's going on associated with this fabric.
Yeah, but voltage is...
It's a property of the fabric.
I'm sorry?
It's essentially a property of the fabric. Now, to clarify for our audience, Peter, what you're proposing here, is this the same thing as quantum field theory, where the quantum properties of field are given through a space? That's what we're talking about, or am I confused?
So I perhaps should have given another link to a video by, I think it's PBS Spacetime. Talks about quantum realism. So they describe this fabric. It would be called, it's a potential. They describe it in terms of, there's something called the Bohmian interpretation of quantum mechanics that you can use to describe the potential or the fabric of space. So that was one interpretation. So he took a very literalist interpretation similar to Bill here, but instead of using ropes, they describe it in terms of potentials, talking about if you have, instead of this fabric, instead of this image here, if you have a capacitor, I shouldn't have erased it, but we'll get back to it. If you have a capacitor, you can describe it in terms of the field, in terms of ropes. Here are Bill's ropes, these electric ropes, or you can describe it. So here you have a charge here, you have Q and another minus Q, for example. You can describe it in terms of like a rope, in terms of ropes. You can just as easily describe it in terms of a fabric where in the two-dimensional representation, it's like a slide. Yeah. The charged particles like to bend towards one fabric rather than the other, and the particles slide from one to the other.
So, Bill, have we reached with this recent clarification a dual rope rag theory of your ropes? I mean, could you conceive of your ropes being a fabric? Could we sew your ropes?
By the way, I would say
his rag
I was
is
just kidding, by the way. Could we sew a cloth with your ropes?
I would say maybe not, but go ahead.
It sounds like the emperor's rag.
Maybe Bill's is the emperor here who doesn't have clothes, but in any case. So